right at the
How you
top.
doing?
There we go.
Okay. How you doing, Bob? How you doing, Steve?
Hi, Charlie.
Yeah. Oh, Bob, good to see you there. Are you still in California, or I thought you were trying to move back to Vegas sometime?
Yeah, we came back to Vegas for 3 months.
Oh, okay. So, I mean, you're back here for good now, or?
We timeshare both places.
Oh, I see. Okay, yeah,
We brought the bad weather with us.
Yeah.
We needed rain.
yeah. Well, it's good to know we have two CW men on the
You
TennaTalk.
got it. I love CW.
Yeah, great. Yeah,
I'm a real nerd,
yeah,
and the band's been great.
yeah. Right. Oh, Charlie, have you fired up your, what they call that RS-918, that thing you brought to Spring Mountain Park there? I just wonder if you had any results with that yet? Because I was thinking about buying it. There's one at AliExpress.
Oh, you mean the yeah,
MCA,
the yeah, 918, yeah, the Chinese radio, the Chinese
Yeah,
SDR,
right.
absolutely.
yeah.
Have I fired it up recently? No.
Sure. Well, okay, Heaven, because they have
Yeah.
one for sale on AliExpress or eHam or eBay, but the seller, if it's in bad shape, the seller pays for the return shipping. That's different.
Oh, that's
than a-
interesting. Okay.
Yeah. So I was thinking maybe that's less of a gamble, because if it is messed up.
So they are selling the new ones, the 918, I think it is, or something
Right.
like that, the 997 or something like
Yeah,
that,
they
the
have
one
a
with the
bunch of
battery
them.
pack. They're selling those new for under $400 right now on
Right.
AliExpress.
Yeah, right.
Uh,
Oh,
So just so you know that.
Yeah, yeah. Well, see, the nice thing is, like, how much do you think that would cost if you got yours and yours was really messed up and you said to heck with it and you're going to send it back? How much would that cost for shipping back there? Would you say?
Oh, it probably $50, 50 or
Okay,
60
yeah.
bucks.
Yeah.
I
Well, that's
would
why
think.
this one seller says that they'll pay for the return shipping.
Yeah.
Most of them won't. You have to pay.
Well,
for
if he's a seller, he's probably in the United States. And I'll tell you, most of those radios are in warehouses in the United States if
Yeah.
they're sold
Oh,
by
yeah.
Baba or AliExpress.
Yeah.
Is the way they've done that. So
Yeah.
you don't usually have to wait that long to get it.
Yeah.
Yeah.
Hey, guys, did you see what Dirk was holding up a minute ago?
What's that?
What do you got?
Oh, yeah. Making me hungry.
Yeah, he's got a noodle.
He's using his noodle.
Ah,
Saw that.
Very good. Way to go, Dirk.
I haven't quite got it on the air yet, but I'm almost there. I just got it.
Have you checked the SWR?
Not yet. I just got it done, and I'm just beginning, but I'm working on it. So I'm gonna work on all that. I got a nano VNA too, and I'll see what I can do with that.
Good. If you need help with it, let me know, Dirk.
What's the best way of letting you know?
You can always contact me. Look me up on QRZ.
Okay.
And the biggest trick I can tell you about the noodle tennas is make sure you've got the windings at the exact same length on either side. Otherwise, you're going to have a hard time getting your SWR down. You'll get it resonant, but you won't necessarily get it down.
Okay.
And the other thing is, little trick, you don't have to actually chop or clip them short, the leads on the ends. You can literally bend it back on itself and to shorten it up. And that's the way you can test to see, get the tuning just right.
Okay.
I hear something ringing, Charlie.
Yeah, no, that's just Matt coming in.
Oh,
I get
okay.
notified of everybody coming in. It's just one of my
Oh, great.
little things that happens to me. So you heard the beeps.
So
I guess I can
let's
turn that
see.
down. And go ahead, Matt, and take your mic off of mute.
There.
And
You
David
hear me
came
now?
in. Yep, sure
All
can.
right.
And also David came in, and feel free to go ahead and unmute yourself also, David.
Got it.
All right.
Hey, Dave.
Hey,
Hey, Dave.
Hey, Dave.
Hi.
Dave's not here.
Good night, Chet. Good night, David.
Good night, Dave.
Good night, Chet.
Mr.
Okay,
Hubsky's coming in.
good. So sure we'll have a few more.
Yep. Go ahead, Mike, and unmute yourself.
Yep, good evening. How you doing?
Excellent, Mike. Thank you.
How you doing,
Okay,
guys?
we're right at the top of the hour, so I think I've got the
Yep.
waiting room completely open, so everybody will just sort of trickle in if they're coming in. But welcome again for the first Monday TennaTalk of every month. And of course, this is a production of the Antenna Whisperer, Rudy Wiedemann, K7RAW, and he will be talking tonight to looking for questions, and he has the answers on getting efficient from podcast 3 that he put up on YouTube. So on that note, Rudy, the floor is yours.
All right, guys, thanks so much. Well, hopefully you brought some questions, clarification questions on podcast number 3, Getting Efficient. And we'll go through those first. Then we'll go through a little wild card on things, anything else having to do with antennas, whether it's podcast 3 or not. Then I'll tell you a little bit what's coming up on podcast 4 Alpha and 4 Bravo. I'm splitting it into 2 parts, and you'll see why here shortly. But before we get going, I do have one announcement, and that is, for those of you who haven't heard, we're going to continue TennaTalk on a Monday night at 7 p.m. on the net, on the KUGE repeater as a network for call-ins, basically, on pretty much any topic. I'll have a couple interesting, fun things to talk about, but we'll be able to talk on that, carry on TennaTalk even throughout the month. And then, of course, on the first Monday, we'll have a special Zoom call like we're having tonight. And so, all right, so let's open it up to clarifying questions on TennaTalk number 3. I've got my presentation up in front of me, so I can bring up slides, and we can refer to anything you would like to refer to. So have at it. Yeah, Mike.
Where you talk about the chokes, it seems to me your discussion on chokes, you should always have a choke at the base of your antenna and one at your rig no matter what. Is that true?
Okay, it is generally a good guideline with a few exceptions. If you understand the purpose of I'm sure you mean the common mode choke.
Yes.
The purpose of the common mode choke is to isolate your antenna from your feed line, to make sure that your feed line does not become part of your antenna system. Especially unbalanced antennas can try to induce common mode current. That means a current that is not balanced or equal on your coax, typically runs down the outside of your coax braid. Okay, that current then can get into your shack, can cause mic bite and things like that. So that's one of the main reasons why you want to typically choke it off at the antenna, especially for unbalanced antennas. It's less critical for balanced antennas like dipoles if it's really well tuned and very well balanced, giving you a very low SWR, which, by the way, that's how you know your antenna is balanced, that you get a low SWR. If you've got one length on your dipole a little bit longer or shorter than the other, you won't get the lowest dip you can. So that's a little hint. Anyway, so if it's a balanced antenna, the need is not so critical. It's always a good idea. But the exception to the rule is when you actually want to use your coax as part of your antenna. And some people use that as a counterpoise, for example, for end-fed half-wave antennas. And then they'll put a choke at the shack to make sure that the antenna does not try to make the radio part of the antenna as well, and everything that the radio is connected to. The other reason, in any case, why it's a good idea to have a choke at the shack end of your coax is if you're getting local noise input that's being picked up by the coax shield, the braid, from local EMI or RFI sources in the neighborhood, and your coax is becoming a local antenna, not part of your delivered antenna, but an inadvertent antenna. If you're finding that, and sometimes it happens, people find that putting a choke on the rig side of your coax can help a lot. Did that answer your question, Mike?
Yes, yes, it did. Thank you.
All right, perfect. Hey, Ron, nice to see you.
Just a follow up on that, Rudy.
Yeah, Steve.
Are you going to have a whole separate TennaTalk just focusing on balance and ununs? Because there's a lot to those. There's different types, and just like you heard, there's different applications of them. So is that something you're planning on in the future at all?
You bet.
Oh.
All right. So since you mentioned it, let me kind of mention give you a teaser of what's coming. We will have a separate TennaTalk here in the future, probably about 2 or 3 down the road, that will actually talk about how to build and test common mode chokes, ununs, and balance, how to wind them, how not to wind them, the do's and don'ts, tips and tricks, and how to measure them properly. There's a lot of misinformation on the web about how to measure balance and ununs, and they make it more complicated than it needs to be. It's really very straightforward once you see it. If you've got a nano VNA, it's a very straightforward thing. So yes, the answer is yes. The next one though, TennaTalk 4A and 4B, is all about impedance matching. And I broke it up for a good reason. I looked at the material I have, and I have a lot of material. I didn't want to break it up in time because the concepts flow so well naturally into each other. 4 alpha is going to be the presentation part, like I normally do. And then 4 Bravo is going to be a live demonstration of SimSmith, and we'll actually give you a tour and drive SimSmith around using some of the examples that will be in the 4 Alpha presentation. So those will be out back to back. And so you'll be able to watch one and then the other right behind it. And that's we're peeling the onion down and getting down to thicker layers of the onion there. It'll be a lot of fun, and it'll be extremely revealing and eye-opening for everybody, I think. Good. Okay. More questions, please.
Yeah, Rudy.
Yeah.
On these clip-on ferrites to get rid of common mode.
Yeah.
How many of those does it usually take to be effective? I mean, some people use 2, some people use 3, some people use 6. 6 is a number?
6 is, I found 6 is the sweet spot. It's the bang for buck. I'll tell you why. What you're looking for, Ron, is you're looking for suppression across the HF band 3 to 30 megahertz of at least a negative 25 dB suppression, common mode suppression. That means that if you inject the same signal through through both sides of the input and hook them up both sides of the output to the other end of a nano VNA, okay, like you're measuring a filter, it would normally, if you had a balanced system, it would normally pass everything through and you'd have nearly 0 dB loss. But if the common mode choke is doing its job, you'll see across the entire spectrum, you'll see that come down. And in one of the future videos, I'm actually going to do that, probably in that same balance and choke, all about balance and chokes. We'll actually take a piece of coax, I'll have it hooked up to the nano VNA, and we'll clip them on one at a time, and you'll see that level come down until it's below 25 dB across the entire 3 to 30 megahertz spectrum.
Okay, one other question. What mix of ferrite should those clip-ons be? Is that 31 or 43 or what?
All common mode chokes should be mixed 31. All
Okay.
balance and ununs should be mixed 43.
31. Okay, thank you so much.
All right. More questions, guys?
I got one, Rudy.
Yes, Steve.
Okay, I wonder if you could go back to your SWR graph where you show the losses for different amounts of SWR. That's handy to do. It's not necessary, but maybe it'd be good to show that.
Okay, so you're talking about the one with the colors on it.
Well, yeah, the ones that for different SWRs, what's the percent loss that you have there?
Got it. Okay. Charlie,
Yo,
help me out here. How do I share my screen?
okay, what have you got up, Rudy? Have you got your PowerPoint or,
I've got my PowerPoint slide that Steve's referring to.
okay, and do you have it set up on your screen? Just go ahead and share PowerPoint. And
Okay,
you probably don't need to share the sound, but go ahead and click that. Don't click optimize at all.
got it.
And then click share.
Perfect. All right, you guys seeing that?
It's coming up, Rudy. Hang on a second. There we go.
Oh, okay, yeah. Okay, I guess the question is, let's just take a SWR of 2 to 1, where the loss is about 11%.
Mm-hmm.
Now, the question I have is, where does that loss occur? Now, let's just say, for example, you got a 100-watt transmitter, you got an antenna tuner, a reasonably efficient antenna tuner, and then you have a 50 feet of coax. Let's say it's like a RG8 size, the big size coax, good quality coax. And then you, at the feed point, you have a balun, and then you have, let's say it's a 40-meter center fed dipole. So looking at that, you know, you're saying there's 11% loss. Where does that 11 watts disappear essentially then in a system like that?
Okay, great question, Steve. It would occur typically at any interface where you have a sudden change in impedance. Okay, that to an electromagnetic wave, okay, an RF signal, looks like a partially reflective mirror. If you had a perfect match of impedance on both sides of that connection, whatever that connection is, okay, wherever that connection occurs, if they have a perfect match, then it'd be perfectly clear piece of glass. That's a good analogy. So what that also means is that if you have an SWR at your rig that you're measuring at 2.0, as opposed to an SWR you're measuring at the antenna or on a short piece of test coax from your antenna outside, but not all the way back at the rig, then that's your SWR there. But it may not be the SWR that your rig will see when you finally drag that full length of coax back to the rig. It might be a little higher. So if let's just assume that it's the rig end that you're measuring SWR of 2 at, then that's the SWR of your total system. That's all the partially reflective mirrors, so to speak, and the losses that they would generate. And you remember that animation slide where you saw the wave coming across and then hitting that interface, and some of it coming back and some of it going through, right? You remember that wave?
Sure.
Then that happens at every interface when there is a slight or some whatever mismatch of impedance between those 2 points at that interface. Did that explain it? Did
Well,
that
I
answer your
guess
question?
the question again is describing what I just, you know, the system where you have your transmitter, the antenna tuner, the coax, the feed point antenna. There's 11 watts. Now, where exactly is that 11 watts lost? I still don't.
Okay, are you guys seeing this?
Yep.
Okay, great. So here's again the generic antenna, complete antenna system from the rig all the way up to the antenna. In this case, it's a vertical, okay, or it could be anything, could be a dipole, whatever. And let's say the rig is measuring an SWR of 2.0. It is the total reflected over the transmitted energy of the entire system out to your antenna, okay? And so that means you've got a relatively efficient system, okay? 11% is not a bad loss, all things considered. A lot of people have more than that and they don't know it. Now, to be clear, Steve, if you went up to your antenna and let's say you put your nano VNA right there at the feed point of your antenna into your common mode choke at the antenna, you would probably have somewhat less of an SWR. Now, what you can do is break down where that SWR is coming from. Where's the losses coming from? If you're measuring a 1.1 SWR right there at the feed point to your antenna, then you know it's got to be, the losses are got to be back up towards the rig, right? It's got to be somewhere in the chain between there back to the rig site, either a corroded connector, or water in the connector, or a loose connector. Loose connectors are the bane of all electronics, so I check there first.
Yeah.
But you know, you can, that's the way to chunk it down.
Yeah, I guess I was reading in a book, I think it's this guy, it's called Reflections. I think it's put out by someone at CQ magazine there. And they're saying that, you know, if your antenna tuner right at the rig there is, it's called conjugate matching. They're saying if you adjust that antenna tuner, that reflected wave coming back will essentially just send that reflected wave back to the antenna if your antenna tuner is adjusted correctly. So that 11% loss, I really question where that would come from, because, you know, let's say at the feed point of the antenna, you have essentially a 2-to-1 SWR.
Right.
So that means, you know, that so that the wave coming from the transmitter to that feed point is going to get reflected back. So there's going to be a reflection back. But as long as the antenna tuner is tuned up correctly, when it gets back to the antenna tuner, it's going to go right back to the antenna. There's no really loss there. I guess that's the question. I don't see the 11% loss there.
Okay, so a good way to look at this, Steve, is to think of a partially reflective mirror where the rig meets your coax, and another partially reflective mirror where the coax meets the antenna. Okay, each one of them has a slight mismatch. What'll happen is you'll pump a wave into the coax at the rig end. That'll go down through the coax. It'll have its own inherent slight losses, and then it'll have a major loss when it hits the antenna because there's a mismatch there, right? So now you have a reflected wave coming back, but only a portion of that will come through to the rig. It'll be reflected back, and it'll end up a lot of it rattling in that coax back and forth. And if the coax was resonant, it could cause some issues, but most coaxes are not cut to resonant length. It'll rattle back and forth, and an antenna tuner, what that will do is it'll try to minimize that rattling back and forth, if you will. The conjugate match is, all they're saying, by the way, is the conjugate match, guys, is the imaginary term of the impedance. Okay, as opposed to the R value, the J value, whether it's plus or minus, in other words, the reactance, the portion of the impedance. If you have a positive reactance, okay, it will interact with that and give it an offsetting negative reactance, okay, and vice versa, so that it'll try to cancel out the reactances and make that system resonant, because a zero reactance is a resonant system. A zero J value is a purely resistive or totally resonant system. Okay, you with me, Steve?
Yeah.
Okay, so that's the purpose when they say a conjugate match. And that's how a antenna tuner, one way to look at an antenna tuner is to try to minimize that back and forth rattling of the wave in that coax. And of course, this happens at every section in the system between impedance mismatch interfaces. If everything had a perfect match, none of that would reflect back. It would all that energy would go through out to your antenna.
So Rudy, I've got a question for you.
You bet.
Based on that discussion, and of course, the picture that we're looking at on the screen right now, where's the best place to have the antenna tuner? Most, I mean, right now, just to preface that, a lot of the rigs have antenna tuners built into them now. Therefore, it's at the rig, and you're talking about your impedance going directly through the coax into the antenna without another antenna tuner. Are you saying that we probably need two antenna tuners?
The answer is I hate to sound like a lawyer, Charlie, but it depends. It depends, right? Okay, so
Uh-huh.
here's what it depends on, okay? It depends on where you either know or believe you're getting the most mismatch that needs matching. Okay, so I would like to propose that you ban the word antenna tuner and call it impedance matcher, because that's really what it's doing. It's not tuning any antenna, okay? Certainly not at the rig end. It's accommodating an impedance mismatch at the rig end. That's what antenna tuners inside the rig are primarily there to do, is to keep your rig happy, in other
Right.
words. Now, if you know or suspect that you have an impedance mismatch at your antenna, okay? For example, between your antenna and your feed line, 50 ohm coax, and you've got something other than 50 ohm impedance at your feed point of your antenna, that's a great reason to have an antenna tuner at the antenna feed point. Now, another reason is if you have a multiband antenna, well, that impedance is going to be different at different frequencies, at different bands. And so you're going to have to change the matchup, the impedance matching circuitry or the network will have to change values to be able to get the best match on a different band if it's a multi-band antenna. And that's the driving motivation for having an antenna tuner at the antenna.
Okay.
Okay, guys, more questions. This is great. We're off to a great start.
Okay, Rudy, let's assume that we've got a antenna tuner right at the rig.
Okay,
And so the rig is happy
okay,
because it thinks it's a 1-to-1 SWR, but it's really not, because you've got a big mismatch between the coax and the antenna.
right.
So now you still have the loss, isn't that correct? You still have the 11% loss or whatever it was.
You do. And
That's
where you have those losses, but those losses, another way to look at it is those losses are not sending power back into your rig, reflecting, shoving it back down its throat, so to speak. And those are basically made up by the losses in the tuner network itself, in the inductor and capacitor network in the tuner. And so that's typically what absorbs that stray power that would otherwise come back into your rig. And that's how you protect your rig.
So
Did that make sense?
let me understand. So if you got that standing wave bouncing back and forth on your coax, that's heating up your coax, and some of that power is being turned into heat?
No,
heat
not
up
so
the
much on the
coax?
coax, Ron. Not so much on the coax. Inside the actual antenna tuner, in the components, it's dissipating heat, especially the inductor. Okay,
Oh,
if you
okay.
and of course, most antenna tuners, certainly automatic antenna tuners, and any antenna tuner for that matter, has a limit to the how high an SWR it will be able to try to match up, how bad a match it can handle. Some are better than others. SGC and others, LDG and STGC, both have pretty good tuners that have a very, very wide range of components, but they'll have circuitry in them. Of course, the automatic antenna tuners have SWR circuitry built into them that measures the SWR, and if it gets too high, the antenna tuner will shut down on you and will say, I'm not going to let this through. I'm gonna shut this down. So it has to protect itself as well.
Okay, gotcha. Thank you.
You bet. This is great. Oh, hey, Craig, you're on mute. Go ahead and unmute yourself, Craig. We cannot hear you.
Okay, I'm on the phone fighting with a credit card company. I'll talk to you later.
Okay, Craig. Craig's calling us from Alaska. So, okay,
I got one more here.
sure.
Okay, and this is, well, if you go to the what is impedance where you talk about like the R plus JX.
Okay, so let's see. What slide are we talking about? Oh, here we go.
Yeah,
I know,
what is
I
it,
got it.
please?
I found it.
Yeah, okay.
This one.
Now, I'm sort of nitpicking here, but it's only because so many of us use vertical antennas here. So when you say like Z equals R plus JX, and you say R is the radiation resistance of the antenna.
Correct.
Now, the thing is, let's say we're using a quarter wave ground mounted vertical antenna, or something like that at least. Now, the thing is, the R there is more than just the radiation resistance, the way I understand it. There's also what's called the return loss that you have in a vertical. So like, you know, let's say if we had a perfectly conducting ground, or we had an infinite number of radials, that return loss would be 0, you know. But, you know, we don't, except for Ron, the crazy guy that was out there, he's 40 radials from his lawn in the middle of the summertime, you know. But for the rest of us, you know, for a finite number of radials, there is that what's called the return loss resistance. So actually the R is, you know, you can look at it like two resistors in series. One is the radiation resistance, and then the other is the return loss resistance. Is that the way you see that?
Okay, well, as I understand it, R has always been interpreted as the radiation resistance. There are other components such as the ohmic loss, and sometimes that's referred to as return loss because it's current that can be reflected back. But the R value in the impedance is the radiation resistance, because let's see if I have it. Yeah, what does SWR really mean? It's in that slide as well, talking about the difference between the ohmic resistance and the radiation resistance. The reason, Steve, that we talk about impedance, it's really focusing on the actual signal or wave, if you will, that is being propagated into the air. And so that's why they take the radiation resistance as R, not the ohmic losses. The ohmic losses, there's some more complex math that I want to go into, but the ohmic losses will obviously increase your SWR.
Yeah, well, I see, from what I understand, the return loss is not the ohmic, you know, like you just like you have ohmic resistance in any antenna because you don't have perfect conductivity. But let's say if you had an infinite number of radials on really good conducting ground, your radiation resistance would be about 36 ohms, usually with a vertical, quarter wave vertical. So that means your SWR would be 1.4 to 1. Now, what happens is, because you don't have a lot of radials in most cases, that return loss resistance will add into the radiation resistance. And sometimes that could add up to 50 ohms. So some people say, oh, wow, I got a quarter wave vertical with a 1-to-1 SWR. Well, really, that's not that great compared to someone that has a much better ground plane, ground, you know, ground conductivity, whatever you want to call it, where the radiation resistance would be to 0, you see. So sometimes that's where SWR can be misleading, because ideally, let's say if he put in 40, 50 more radials into his lawn, his quarter wave vertical in the backyard would have maybe a 1.4 to 1 SWR, simply because he's getting rid of most of that return loss resistance. So it's a little tricky. I think people sometimes, you know, get too wrapped up with SWR and they don't look at the different components there, and it can be a little misleading, I think.
Well, you know, Steve, you know what they call a device where you can have a perfect SWR and you're radiating nothing. It's called a dummy load.
Yeah, right.
So just because you have a perfect SWR doesn't necessarily mean you're radiating. So the and the other trick is, and that's why, by the way, at the end of that presentation, let me just look down here. One of the last slides I talked about the artificial ground. sometimes called a ground tuner or artificial ground. That will actually help in those situations where you've got a very imbalanced antenna between your whip and your ground plane or your radials or your counterpoise. If you've got a very imbalanced state, you can actually help that out, balance it out, kind of like balancing a scale, by maximizing the current into your counterpoise, for example. And that will really reduce what I think you're referring to as return loss, for example. Another trick you'll find, by the way, is if you want to know how good your vertical is, or actually how good your counterpoise is doing, or radials or ground plane, whatever you're using as an artificial or real ground for your vertical, set up your vertical to exactly the theoretical resonant wavelength, actual length, quarter wave, okay, 234 divided by the frequency in megahertz, and then see what your SWR is like. If your SWR is off, chances are you're going to need to somehow tune your radials. And it turns out that if you've got a short radiator, okay, at least from an RF perspective, if you got a short radiator, you'll find that it will work better. Your SWR will come down by lengthening your radials or counterpoise. Okay, if you don't have to lengthen your counterpoise and you're at resonance, then the only thing you might want to do is tune it up a little bit and increase and maximize the current into that counterpoise or those radials. And of course, the other trick is for elevated radials is to droop them down. That'll get your radiation resistance from, like you said, around 35, 36, and it'll actually raise that up with drooping it down 45 degrees, which you'll see, not so uncommon, will actually very straight away raise that impedance right close to 50 ohms. You get almost a perfect match.
Okay.
Great question, Steve. And I will look up the more technical definition of return loss, and we'll hit that in a future video. So more clarifying questions, anybody, please.
Well, you know, a lot of the stuff that I read about verticals, Rudy, is that if you have an elevated ground plane vertical, it's very important that the radials be cut to frequency. As opposed to if you have a ground mounted vertical, the radials that are laying on the ground or maybe an inch below the ground surface do not have to be cut to frequency. In fact, they say it's better to have a large number of short radials as opposed to just a very few long radials. And I always found that to be very mystifying to me. Why? Just because the radials are laying on the ground, it doesn't seem to be that important that they're cut to frequency.
Okay, well, that's a good insight, Ron, actually. It comes down to really a distinction between what you consider a ground plane and what you consider a radial or counterpoise. And it's kind of a subtle and confusing definition. In the case of a true ground, okay, it's like an infinite surface, because you're creating a lot of surface area with even short radials, but you're creating a lot of surface area for that field to dissipate in the ground, okay? Whereas if you've got something not connected to the ground, like an elevated radial or counterpoise, then you're not going to be able to take advantage of that multiplicative effect of the area that you're creating as a reflector to your vertical whip, because that's what it's really doing. It's a reflector. It's like a mirror, and it's trying to make a mirror image copy of the vertical whip to turn it into a dipole. That's essentially what, in fact, in electromagnetic theory, it's called the method of images. And you do the calculations with using that trick. So when you've got an elevated radial or a counterpoise, then you're counting on them and them alone to really do all the work of creating a field, okay, that counteracts the field you're radiating with the vertical whip. And so you need at least 3 or 4 of those, and it's very advantageous to have those cut to the frequency you want to operate on. Or you can have, you know, several of them for each band and have a lot of those radials. Some people, they use, like Paul, RKO uses guy wires as his elevated radials, okay, on a down drooping angle, naturally, because they're used as guy wires. Well, that's a wonderful way of killing 2 birds with 1 stone. You get guy wires and you get elevated radials, and you don't want to connect those to the ground. You want them elevated off the ground as much as feasible, just like you would with an ends of an inverted V.
Yeah, like for my backyard ground mounted vertical, some of the radials are actually, I use sheets of chicken wire fabric.
Yep.
You know, chicken coop fabric, just buried below the rocks. Because, you know, I figured, well, that'd be a good reflector.
I've done very much the same thing, Ron, on an antenna I had in the back. I actually showed this to the club when I first moved here, in my backyard that looks like the surface of the moon. Is putting out a couple of rolls of aluminum window screen. The plastic window screen doesn't work very well, I'll tell you. But the aluminum stuff seems to work pretty well. And it's like a car. Why does a car work, right? Because it's a big enough mass of metal. And in fact, how does my e-moped work? It's a massive metal. And it's not even ready. It's not cut to length, that's for sure. And it's not uniform, that's for sure. It's just a big chunk of metal. It's a counterpoise, right? And the tires make it isolated from the ground. So it's an elevated counterpoise. That's what the scooter frame is doing. And it actually works reasonably well. I can tune up the tuner on the radio just very fine and get a great match quite easily. And even without it, I'm still getting a matchup of about 2-to-1 SWR, even without tuning it.
Yep. Hey, Rudy, I wanted to ask a question, please.
Yes, sir.
Yeah. Okay. Yeah. I finally finished chewing out the people over in Bangladesh with my credit card, which didn't do any good, but I felt better anyway.
How's the weather in Alaska, Craig?
It's fine. We've got about 4 feet of snow drifts out on the porch, and definitely a little bit cooler than when we were down in Pahrump. But we'll be back down your way in time for the club meeting. So we'll see you live and in person here in a couple of weeks.
Okay, great. So what's your question, Craig?
All right. Well, with radials, because they're typically exposed to people or animals, unless they're buried in the manner that we were just hearing about, what sort of RF hazards are there to exposure, both direct radiation or also voltage differences depending on the frequency and the SWR that a person or an animal might encounter if they get across them? Do you follow what I'm saying?
I follow what you're saying. I would say you need to take the same precaution that you would of not allowing people to have contact with your antenna anywhere, because the idea, especially elevated radials, it will be radiating. Now, if they're very ground radials, the earth is going to absorb all that and dissipate any of that current. Okay, that's the idea of a ground radial. But if it's not connected to the ground, if it's a counterpoise or an elevated radials, it will radiate. And think of it at least like mic bite. Okay, RF mic bite. And so you definitely want to keep them flagged. You want to keep them raised up where kids don't run into them while playing soccer, that sort of thing. So safety is an important factor. And so, yes, if you're pumping out a lot of power, then, you know, a good chunk of your power is going to be radiated by those radials. And
I know it makes quite a difference. An experience, I think I may have told somebody this before, when I lived up in Fairbanks, I had a 4080 trap dipole, and we had a lot of ravens, and they would love to perch on the thing. And of course, they're large, they're heavy, they're not housebroken. There's just a whole lot of reasons that you don't want ravens on your antenna. So my initial thought was, well, I'll simply run a lot of power into it and run them off. had no effect at all because the SWR was good. There was virtually no voltage difference between the left foot and the right foot on the Raven, so it was not a problem. So I said, well, all right, let's apply some antenna physics to this. So I hooked up my Tempo 6 and 2-meter amplifier to the thing, which is a tube amp. This wouldn't work with a solid state amp because it would fold back or you blow out the transistors or something, but a tube amp, you can abuse them, and put a lot of high power 2-meter into the 80-meter dipole. That worked great. You had high standing waves, a short distance between the 2 feet, major voltage differences, all sorts of incidental radiation. And so had ravens taken off with smoke and feathers. And after a couple of that, they never came back.
Well, you know, there's a really cool trick you can do, Craig, and that is take a fluorescent bulb, one of these old-fashioned 2 fluorescent bulbs, and you can go up and down your antenna, either your radial or your vertical whip or on a dipole, and you can find the node. So for example, here's a great, somebody showed this to me, it was really cool. 40-meter dipole running on 15 meters, okay? The 3rd harmonic. And you run it up and down and you could actually see where the standing wave nodes were and on where it was brightest and where it was dimmest. And you could actually map it out by sliding it up and down the antenna. You should try it sometime. It's a lot of fun. Pretty
And
cool.
a very visual version of lecture wires.
Exactly.
Mhm. Thank you.
You bet.
So Rudy, when you were talking about the antenna guy wires coming down and isolating them from the anchors, why would you want to do that? Wouldn't you want that? I'm thinking of electrical counterpoise all the time. And for us, it's always you bury it and have a good low ohm counterpoise. Why would you want them isolated on your antenna?
Primarily to control the length, the electrical length of those, the counterpoise wires. Okay, you're trying to create a resonant field underneath your vertical whip that the radiation from the vertical whip can sort of springboard off of, if you will, in kind of a crude sense. And so when you do have when you're using elevated radials, okay, you want them cut to length. That's why there's a big distinction between that and when you've got ground radials to create a real effective RF ground. Okay, the lengths of those is not nearly as important as the area coverage. You want to have a lot of area coverage with that when you've got it buried in as a ground plane, creating a ground plane.
Okay.
Good question, Mike. Okay, what other questions you guys have, especially on TennaTalk 3? Getting efficient. Anything else you want to talk about getting efficient? Don't everybody talk at once. Okay. By the way, I hope you enjoyed the picture of my e-moped QRP rig. So did everybody understand what was going on here with this slide? Everybody get that one? Because it's a little complicated. Yes?
I think so. You've had it before, so it kind of was a reinforcement.
That was the general idea, because I reinforced it because it really is a lot going on. And we'll actually come back to this in future podcasts because it triggers some very useful things to learn about. Okay, did everybody get or follow along my my little calculation here about why the impedance ratio of a unknown or a balun is the square of the turns ratio? Everybody get that one?
I don't know. I think I had a headache, so I had to get an aspirin.
And if you didn't before, you did afterwards, right? Yeah.
Well, Rudy, I'm too old to understand that because for me, voltage is represented by the letter E, not the letter V.
Yeah, you could definitely call it E, call it V. But there's really, guys, this comes out of three basic concepts, right? The first concept is that we all know in transformers that the voltage ratio from the primary to the secondary equals the turns ratio. Everybody remembers that from transformers, right?
Right.
And the next thing that everybody remembers, I'm sure, is that the power across the transformer has to be conserved. So the power in pretty much has to equal the power out, which is generally true for most efficient transformers, modern transformers today. Might not be perfectly true, but good enough for government work, 99% plus efficiency. And then the only other two things you have to remember is Ohm's law and the fact that power is equal to current times voltage. You know those four things, you can derive this, you can walk through and satisfy yourself that that's true. But I'm just saying that a lot of people ask, well, why are balance and unknowns 9-1? 49-1, 4-1. It's always some square number. It's the square of the turns ratio. That's really what it comes down to. Now, you can flip that around the other way, by the way. If you measure with your nano VNA, you've got an antenna that needs an unknown, and it's got a radiation resistance of, say, 300. Okay, that's 6-1. Well, you can't find a 6-1 unknown off the shelf. There's no such thing. So what do? You wind one. What's the square root of 6? It's going to be 2 point something, right? 2.6, 2.7, something like that, right? So you just make the turns ratio 2.6 or 2.7, which means that on one side, you're going to need to have a few turns, and the other side, you have a bunch of turns. You're just going to get pretty close, and you'll be a lot closer than 300-1. You might, in radiation resistance might come down to 60 or 70 or something like that, which will give you an SWR 1.2, 1.3. Great, a lot better than a SWR of 6-1.
Rudy, a question: if you're going to wind your own, is there any rule of thumb on what size ferrite core that you use, depending on power you're running?
That's a great question, Ron. We'll cover that in great detail in a future one, but for today, generally you'll find that the FT240, which is 2.4 inches outside diameter, okay, very common ferrite, and probably one of the biggest ferrites you can get easily, will work just fine with probably, I would say, a 14 or 16 gauge wire, like magnet wire, to wind on. Okay, and if you're running 100 watts, you can do 100 watts with that just fine. If you're running 300 watts, you might want to double up on that and stack two of them together and wind them both together. There are other techniques for much higher power. I don't want to get into right now, but hopefully that gets you in the ballpark.
Okay, thank you.
You bet. More questions, guys? We're just warming up. So do you guys have any questions about podcast 3 before we just throw it open to wildcard questions now? All right.
Rudy,
Yeah.
you listed a G5 RV as an unbalanced device. What is a G5 RV?
Okay. Now you're testing my memory, because
It's
G5
a
RV is
dipole.
it's a dipole, and it is fed with ladder line, typically 450 ohm ladder line, and it's typically an off-center fed dipole fed with ladder line. So what does that tell you? You're going to need to match that ladder line to your 50 ohm rig somewhere, right? At the rig generally. And that usually means some kind of an antenna tuner that has, usually they'll have a balun in it, all right? Because the ladder line is balanced. Then you have to ask yourself, how are you going to deal with the imbalance between the balanced ladder line and the imbalanced antenna? You might need a balun up there as well. And that's actually an unbal instead of a bal-un, if you will. But that's for people who get persnickety. But the most basic one is, as memory serves me correctly, is a balun at the rig end, all right, to accommodate the 50 to 450 impedance mismatch at the rig to your ladder line, and then a ladder line to off center fed. There's a lot of information on the G5 RV, and I'll be honest, it's been a while since I've looked at one, and I don't remember all the exact lengths and ratios and particulars there, but I do know it's open ladder line fed, which these days, not a lot of people use open ladder lines because all the rigs are 50 ohms. They have the antenna tuner built into them. And the other thing is weather. The ladder lines are subjective to weather. And of course, we don't have any weather out here. It also is subject to even swinging around and getting close, changing its SWR just because it swings in a breeze and gets close to something metallic. It's much more sensitive than coax. Coax is pretty tolerant of that.
I used ladder line when I first got licensed. I had a Johnson Matchbox, and it works great, but you have to be located physically where you don't want any sharp bends in the ladder line,
Right,
and going by metal objects and things like that. So when you have the right physical location for a ladder line, they work really good. But we get sort of spoiled with coax, because coax you can run almost anywhere and it's not affected. But with ladder line, you have to really, you ideally would like to have it going straight down from your antenna and all that. And for a lot of people, they just don't have the physical situation for them to set it up, it seems like.
Yeah, it's you're absolutely right, Steve. And the other thing about ladder line is it's actually more efficient in terms of losses. So people who are really into shortwave listening and SDR radios and stuff like this, they like to use ladder line because if they set it up correctly, they'll actually do better with pulling in some really weak signals, because it is more efficient than the average coax. Maybe not LMR 400, but RG8X for sure. It's more efficient. Okay, great. What else? So let's talk about anything antennas. What's on your mind about antennas? What do you want to talk about? Steve.
Yeah, I just in the process of building a portable antenna. I'm using like some PVC pipe for a base to stick it into, but I'm going to use like one of the whips that you use that extend out to like 17 feet. And of course, you're sort of in a way, getting it from China, you wonder how durable those are. So I ordered 2 of them, but you've used those whips quite a bit. How is the durability of? Do they hold up over a period of time? If you're careful, obviously, how you use them and everything. Or after a while, do they start to slip a little bit? Let's say you adjust it for 15 meters, and then you start operating, and all of a sudden the SWR goes up because the whip starts to slip down and it turns into a 10-meter antenna or whatever. But what's been your experience with those whips from China?
Steve, I got to tell you, I've been pretty happy with them. Slipping has never been a problem with them. On the contrary, they can sometimes get a little sticky to adjust, especially if you're doing some fine tuning of a section. And what I simply do is I twist as I pull it in and out. I just give it a slight twist as I'm doing that, and it breaks free and gives me a nice smooth tuning action when I do that. But I've never had a slipping problem. Now I will tell you, I broke one, bent it beyond recovery, mainly because the antenna mast fell over on that end of the dipole, and didn't look so good afterwards. So it's now my dedicated 10-meter antenna. So be careful with those really thin parts. And remember, there's 14 sections typically on those things. So if you're trying to get it all the way out and there's only 13 sections showing, it's probably the little guy still folded in there. You have to pull them out. And so just be aware of that.
Yeah, I'm hoping to go out Saturday and test it out and see, try different bands and see how, when you can tune it just by pulling it up and down. So it sounds like a great thing to have if you want a multi-band, easy to put up portable antenna. So I know you're the one that showed it at our meeting, and I eventually said, well, that sounds interesting. So I'll try it out this weekend, see hopefully if it works.
Well, good. Well, I tell you, I eat my own cooking.
Yeah.
So it works for my moped mobile rig. And so I wanted to ask you guys, are you guys all coming to the antenna shootout on the 22nd? You all know about that, right? Anybody not know about it?
Yeah, I thought I'd warn everybody, the day before is my birthday, so I'm gonna celebrate the next day by kicking everybody's butt with my antenna. So
Good for
don't
you.
anybody get their hopes up.
I welcome that challenge, Steve. I welcome that challenge.
Okay, Rudy, we are approaching the top of the hour.
Okay.
And also just on that shootout, you need to send me a little something so I can get my spam out.
You
And-
betcha. I'll send you the full
Yeah.
data sheet on the details.
Okay, good.
Bring your antenna and let's try it out in the field, out open in the clear. Where there's
Hey, Charlie, can I make a
relatively
brief
low noise.
announcement?
Sure, go ahead, Craig.
Okay, on a few days after that, April 15th, we have some visiting hams, including a gentleman from Japan who's coming over to Pahrump for an all-day tour of the Restoration Center and everything else of interest over the hump. So anybody who's interested in going along with us on the tour, save tax day, April 15th, that's Saturday. And we're going to be going over to the Experimental Aircraft Association chapter at the airport, seeing some experimental airplanes and gyrocopters, going to the museum, seeing the station there, going to the Restoration Center, going to all the things that are worth seeing over the hump. So if you want a guided tour, I'll be happy to get you on board. Again, that is April 15th, Saturday, a couple of weeks from now.
What time is
Very
that, Craig?
Well, whenever you want, not too early, but because I'll be coming in after a time zone issue, but let's say around 10 o'clock.
Okay, great. Yeah, interesting.
So just stay in touch. All my contact information is good on QRZ, and including both the Pahrump phone numbers and the ones here in Alaska, or email always works, and I'd be happy to have you on board. Be great to see you.
That's great. Thanks, Greg. Okay, folks, before we wrap, are there any other last minute questions?
I have one, Rudy.
You bet.
On your noodle antenna, when you did your wrapping of your wire and connected to the coax on the inside, did you bring the coax out and solder it on the outside and shove it back in, or did you pull the wire all the way through and to the far end and then pull your coax back up with the wire?
The latter.
Okay. All right.
That's a lot easier that way to just pull the wires, basically feed the wires through the holes in the PVC in the middle of the tube, and then pull them out the other end, solder it there, and then pull them back until the coax came up to the inside of the hole.
I was thinking that if you did it the other way, you could have enough, it naturally comes off the spool spiraled, so you wouldn't have to re-spiral. You'd have perfect little spirals.
Well, yeah, I guess you could do that, but it's a trade-off, whatever works best for you. But as long as you understand the principle. And by the way, on the noodle antenna, as it turns out, I did some extensive experiments. It does not matter whether you wind them together in the same handedness or in opposite handedness on either side of the feed point. So you can either have them going this way or you can have them going that way. Doesn't matter.
Okay.
It shouldn't. Very good. Rudy, thank you very much again. And we look forward to next month's little question and answer session. In fact, actually, it sounds kind of good. Are you going to do both podcasts 4A and 4B at the same time, or present them at the same time up on
I am.
YouTube?
I'm going to post them at the same time because if you have enough coffee and had a good night's sleep, you'd probably be able to watch both of them back to back. Probably would want to, because
I do it the other way, Rudy. I usually do it fully encased in some sort of adult beverage.
you're probably better prepared then to absorb it.
Yes.
But anyway, yeah. So
Okay.
I'll have it in two parts, and so that either one you can chunk it down and take a break, and then come back to the other one. And you'll find, because they dovetail together, they're interlocking. They really reinforce each other, and that's why I want to do them both. So it'll be a double whammy session next month.
Okay, very good. Rudy, thank you very much. Everybody online, thank you for coming on board, and it is a pleasure to see you guys. Hope to see you at the meeting on the 19th, our next general meeting. And until then, 73, everybody.
73,
Thanks a
guys.
lot.
Thank you.
Take care.
Bye.
Bye-bye, guys.
Bye-bye.